So, the conclusion of our conference, the final talk, reliable microservices from the famous, legendary social network Odnoklassniki participant Oleg. Please applause to our speaker who will try to fit 45 minutes talk into 35 minutes. Oleg,
okay.
your stage is on fire. Please.
Hello, everyone. My name is Oleg Anastasyev, and I'm principal engineer in OK.ru. Let's start our talk today from brief introduction into OK.ru. We are the most popular social network, not only in Russia. Here you can see our top 10 countries by audience. Numbers show monthly active users in each country. And I'm very proud that Armenia is one of our top 10 here. From the engineering perspective, OK.ru consists of 9,000 hardware machines running almost 50,000 tasks. Almost all these tasks are running in containers in our 7 private clouds. About a fifth of these tasks are combined into 300 unique performant microservice clusters. And now we'll try to build one of the services together, a messenger or chat service. So, in a typical messenger, a user could have a list of conversations or chats. An average user actively participates only in a limited subset of all these conversations. Our stats show that only 5% of conversations generate 95% of requests to the service. Most of what data messengers store are, well, messages. In most cases, only up to 13 of freshest messages are seen and so be requested from the messenger's data store. But these don't apply when getting the freshest messages of each conversation to render it next to chat name here. These messages are uniquely to be requested for the unlikely to be requested for the second time. When rendering a web UI, a first message is retrieved for each conversation and shown next to conversation name. For mobile UIs, freshest messages are retrieved for all conversations stored on a user's device. Let's aim to store at least 500 billion messages inside 5 billion conversations. All this would take about 100 terabytes of data, not counting a replication yet. This new service should sustain more than 100,000 reads and 10,000 writes per second, with latencies of a single millisecond scale. Every modern messenger should have full text search function, so when some search text is entered here, we'll find conversations and messages containing it. And this means that messages should be reiterated to build a search index. Messages have not only text. Here we can see some simplified message table with the conversation ID here, ID of the message within conversation, the author of message, the message type, finally the text of the message, and the list of file or picture attachments to the message. So messages in our service can be represented with a table like this one. And messenger service must implement the following operations. Get messages. Gets messages in the specified chat for the defined user. It can return different messages for different viewers because of the selective message deletion, appropriateness filters, and so on. That's why the viewer is among parameters to this method. Most of requests to the messenger service come to this method. So it should work as fast as possible. Get last messages gets a single last message for a supplied list of chats to render the freshest message for each chat in the conversations list. This one is the most heavy operation of the service. Multiple chats should be traversed to get the last message of each one. Add operation adds a new message to some conversation. Search is a full text search in user's conversation, and index messages operation builds an index for the search to use. Let's try to build this messenger service employing the modern microservice architecture, of course. So users using their mobile phones or web browsers, either directly or using some front-end servers, communicate with the messenger service. The messenger service runs application logic for the service. The application state or data is stored separately in the dedicated database store, and it is fault-tolerant and highly available, of course. To achieve this, a database could do some sort of replication, so it's distributed, replicated, and so on. But let's leave it out of scope for a while for simplicity. That's it. Let's try to go live and see how the most frequent operation, get messages, could be implemented. To get it down, the query like this should be executed by the database. The problem here is that this query should be executed 100,000 times per second by the database, which generates some load to the service. Well, scaling is what microservices are all about. Let's start more instances of the service. And now we see that instances of the service generate more requests to the database, and how the database, now the database is overloaded. What's next? We could either scale the database or make use of the knowledge that only 5% of data are hit by the majority of requests. Let's cache some. And the database definitely have a cache we can configure, but it turns out that database cache is not effective enough. It caches a lot of unused rows. This is because of these operations of the service, the get last messages operation and the messages indexing process are reading not only 5% of the actively used conversations, but all 100% of conversations. And this operation are very rare comparing to the get messages, but because they touch all conversations, all of them hit the database cache, flooding it with all those 95% of rarely accessed and useless to cache data. The database cache is typically restricted to the few generic implementations. The least recently used algorithm is the most popular here. And the database cache typically can be adapted for application logic to control which data should be cached and which should never be. So either we should throw much more memory to cache all this rarely accessed data in the database cache, or be able to implement an explicit cache management logic in the application. So only messages which should be cached are cached indeed. Let's introduce the memcache service for this purpose. This takes a load of the database. When the load increases, we can scale memcaches independently from service instances and the database. And this way, we came to the typical modern service architecture many of us are familiar with. So let's delve into costs hidden in it with more detail. So the first is the CPU cost of the marshalling and unmarshalling. This is the process of transforming the memory representation of an object to a data format suitable for storage on transmission. To make single request to the memcache, the application logic marshals the request and its parameters. Then the memcache unmarshals this request to its own in-memory representation. After the memcache processes the request, it marshals the response. The application that unmarshals it. These marshalling costs also apply for the application communicating with the database. Intuitively, we tend to think this cost is negligible. The right thing to do is to measure it for exact system, of course. In this talk, I'll use measurements and results published in the excellent paper named Fast Key Value Stores, an idea was time has come and gone, from the group of researchers from Google and Stanford universities. Please read if you are interested in how this measurements was made. So according to these measurements, this cost could add a fair amount to CPU load and can constitute almost a third to a median latency of the system. The second is the cost of overreads and overwrites. These are costs of reading or writing more data from the cache than it is necessary. If it stored last 13 messages in the memcache packed to a single blob for each conversation, to render the list with a single freshest message text to each conversation, we'd read a blob containing all 13 messages for each conversation, marshal it, transfer to the application, unmarshal to individual 13 messages, and just throw away 12 of them as useless, except the freshest one. The same paper states that if only 10% of the data is used from the retrieved data, like we have here approximately, we can expect almost half of CPU and dramatic piece of the network traffic wasted by overreads. The third one is cost of the network-related latency. Each request-response pair to both the memcache and the database introduce the round-trip time latency, or RTT. The additional delay adds up for moving the data over the network to or from the memcache and the database, and vary a lot depending on the size of the response. But the worst thing is here that latencies are multiplied by the number of network requests the application logic makes to serve a single user's request. For the get last messages request, a separate request for messages of each conversation must be made to memcache, multiplying a single application request to tens or even hundreds of memcache requests. Well, as we can see, costs are high, but how can we lower them? Most of the load naturally fall to the memcache and its link to the application logic. So these costs are much more visible here, and most efforts in industry are spent on optimization of memcaches and their link to the application logic. For instance, Redis and Tarantul are trying to fight over reads by introducing data structure in the memcache, allowing application developers to request only necessary subset of data. Netcache fights network latencies by introducing the in-network caching embedded into the network switch infrastructure. The KV Direct is about to lower CPU costs by placing marshalling onto the network interface card internal processor. We'll try to optimize it a bit from a different angle. These costs are introduced by the sole remote location of the application state. So we can get rid of them by moving state closer to the application logic. This way, we come to the idea of stateful microservices. A stateful microservice combines the application logic with the custom in-memory store in the memory of the same single process. And so network latency costs are not applicable here anymore. This in-memory store is custom. It has the application-specific logic implementation. This allows an application developer to implement a service application logic without overreads. CPU costs of marshalling could be eliminated or lowered significantly, selecting the appropriate application-specific data format for both components. Embedding distributed persistent store code to the same process eliminates the same costs on the second leg of the architecture and allows us to easily integrate all components. Words embedded and distributed next to each other could be a bit mind-blowing, but what I mean here is that we embed the code of the distributed store, so the code runs within the same process. An instance of stateful service then becomes a normal node of distributed store, participates in distributed nodes cluster, stores data on the local machine's persistent store, and does all the necessary operations just like a dedicated distributed node could do. This way we get a more efficient stateful microservice, and it's always more efficient than the same application implemented as stateless service because it has no more cost to pay for external location of the application state. Let's also see how the statefulness affects the fault tolerance of the service. For this, let's consider what distinct failure scenarios could be in the simple distributed system of two communicating parties, the client and the server. The client sends a request message, the server processes the request and sends the response message back. The client can send a request and disappear from the network. The server can disappear as well. They can crash or reboot, or their hardware can fail and hang. A request or response message could be lost. The network is failing, buffers overflow or on either communicating party. The server could time out. A response is sent beyond the defined timeouts. The invalid value response, the server responds with a message the client cannot understand. How could this happen? Easily. The server is running fresher version of the software, but the client runs obsolete one. And finally, the arbitrary or Byzantine failure. A party makes arbitrary messages at the arbitrary time. This could be some bad intention actions like DDoS attacks, or it could be bugs in the code and so on. I'll talk more on this how to deal with failures in the upcoming talk, distributed systems at OK.True tomorrow. Thanks to Armenian C++ and system design community. Please come if you are interested. So a total of 7 failure scenarios are possible. Let's try to apply them to both stateless and stateful architectures. Let's take a look at the stateless service first. A user sends a request message to the application service, and service processes it, sending requests and getting responses from both the memcache and the database over the network. So here we have pairs of the simplest distributed systems. The first one consisting of the microservice and the memcache, and the second one, the microservice and the remote database store. What makes things worse is that failures to the memcache and the database are not unrelated to each other. So we must consider how failure to the memcache will affect part of operations working with the database and other way around. So these failures are bound to each other and must explicitly be addressed by an application developer. So we have 7 failure scenarios here, another 7 to address on the database, and we have third simplest distribution system here between the user and the Microsoft itself, with another 7 failure scenarios to address. All of these failures are bound to each other, so an application developer must address all of them, plus their combinations when a failure in one component affects operations of or state of another. This adds some complexity to the code, making such failure handling harder to implement and debug. Let's now take a look at the stateful service architecture. There are same 3 machines, but their layout would be different. The sharding scheme would be different as well for the stateless architecture if each of 3 machines is responsible for some set of keys, K. When going stateful, each of the machines is responsible only for the third of the original concept, each for its distinct subset. A user communicates directly to each stateful service instance, making the same 3 pairs of communicating parties. On each of them, the same 7 failure scenarios are possible. The only difference is that these scenarios are unbound to each other and not unique, because all 3 instances are implemented as identical components. So addressing failure scenarios here is easier. Such failure handling can be implemented uniformly for one pair and will work the same way for all others. To further evaluate reliability, let's compare probabilities of the full downtime. For the stateless service, downtime of any component, the memcache, the database of the service itself, leads to inaccessibility of all keys. So the probability of the service downtime for keys from the full key set can be calculated like this. For the stateful service, downtime of a single machine lead to inaccessibility only of 1/3 of the case. Only when all 3 machines go down, each one with its own 1/3 of K, there will be inaccessibility of the full set of the keys. So the downtime probability for the full set could be calculated like this. Which one is better is not obvious looking at this formula, so let's try to evaluate them with numbers. Let's assume probability of a single machine downtime is 1/10. This is very high probability, of course. In real life, they are much smaller than 1, but let's take this number for simplicity. When we have these 1 numbers for downtime probabilities, the smaller number is the better. We see the downtime probability for the stateful microservice is orders of magnitude smaller. In real life, people use replication to reduce downtime, so let's set up replicas for each of the components on the left. Installing the second replica reduces downtime probability of a component by an order of magnitude. Now we have allocated 6 machines for the stateless service. In this setup, more reliable than 3 machines from the right. Let's do all the calculations with few numbers. Actually, no. Failures are still bound to each other, so both replica failure will still lead to downtime of the full key set. Okay, let's go to the implementation of this idea. So, what to start this from? We want our service implementation to be highly available, so a replication must be supported and consistency guarantees between replicas must be defined. And we know our service to be scalable, so when load to our service increases, we could scale it by adding more instances. Now our application and its state are collocated, so it must implement resharding of the state of the data among newly added instances. All this could be implemented from scratch, but these parts are really hard to get right. Instead, let's find something ready to use. All these words, application, consistency, guarantees, and resharding give us a hint to seek this in modern distributed databases. So first of all, let's decide which one code we would embed. This database must be implemented in the programming language of the application logic to make a code reuse simpler, avoid marshalling costs, and simplify an integration of components. It also must be open source, so necessary extensions of a database functionality could be implemented. OK.ru mostly used Java for our applications. We had successful experience running Cassandra database, so we choose it as the database for embedding. The first step is to embed Cassandra, is launching it in the same JVM together with our application. Looking at the startup scripts, we could easily find the Cassandra daemon class. It manages lifecycle of a node. So all we have to do is include necessary libraries to the class path of our application and start the Cassandra node by this code. Cassandra YAML here is Cassandra. That's it. Now we have the database node running in the same process. When started, it will read its configuration file and join the Cassandra cluster, just like it was started by standard startup scripts. So as now we have the state collocated with application, let's look how it changes the client request routing. So here we have our user, his name is Luke, and he's about to participate in the conversation, which key falls into some set B. Luke uses some front-end system for this, that's why I rounded him with the green rectangle. For the stateless service, there is no difference to which available instance to send a request to. The front-end could make a request to this instance or these instances. For all these instances, cost of serving a request of a key from the set B is equal. Some network requests must be done to remote mem caches and databases to get the necessary application state. Contrary to stateful services, every instance has some part of keys stored locally. Leftmost instance of some set of keys A, second owns B, and the rightmost owns C. This way, the instance owning the set B does not have to make a network request for the data. It is either in the memory of the instance B process or it can be read from its disks. Other instances cannot set B data locally and have to make network requests for it. The cost of processing Bs are higher because now should include costs associated with marshalling and network latency. So to make the processing effective, clients must route their requests directly to the instance owning the necessary data and avoid routing their requests elsewhere. This is possible if clients are aware of the cluster topology. I mean information about states data partitioning across cluster nodes. Such client routing could be implemented on the front-end system in the form of a library. This library route requests directly to the nodes owning appropriate data partitions, so these nodes can process requests accessing the local data only. Data partitioning is the sole responsibility of a database, and we have the Cassandra code embedded. Let's take a look how Cassandra partitions data. Every row in Cassandra has a primary key composed of two components. The partition key is used to determine the node owning the data. The clustering key is used to define the order of rows within a single partition and has nothing to do with the data partitioning. Rows with non-matching partition keys fall into different partitions and could be owned by different nodes potentially. Rows with non-matching only clustering keys are in the same partition and will be placed to the same node ever. As in the messenger application, the order of messages within the single conversation is important, but order of different conversations between each other is not. We select the conversation ID as a partition key and message ID as the cluster key. There are following components in Cassandra code responsible for the data partitioning. The partitioner, given the partition key, calculates its token, usually applying some hash function to it. All possible token values are usually depicted as a ring. The partitioner is defined for the cluster once and can be changed in future. This whole ring is then split by token ranges. Mapping of ranges to primary nodes is stored in the token metadata. And the final component here is the replication strategy. It defines how to select nodes for secondary replicas of data and how many of them should be at all. Different replication strategies could be configured for different tables. That's it. This information is enough to get mapping of all data of the cluster nodes by this simple code snippet. The endpoint map here is exactly this. It maps max token range value to all the replica nodes addresses. Transferring this map to the client, the partition-aware routing can be easily implemented. Then also to consider is that topology is not constant and can change over time. Some new nodes join the cluster, some other nodes leave. So this map refresh could be implemented in clients. Well, clients now wrote a request to the data to the right nodes. Let's look into how these nodes work together with this data. So messages are stored in kind of this table, and we are about to implement get messages to get list of messages within a conversation, so it should execute a query like this. To execute this query using data stacks client drivers, we should use a code like this. You can find this code in the Getting Started manual of their GitHub page. So the first line is a connection to the database. The second line sends the query of the network and retrieves the result set. In third line, the data is used then. And connection to the database is closed. This is hidden in the final part of the try with resource statement. In real life, this could be more complicated. Management of connections, the configuration should be retrieved from somewhere. Some connections fail, or handling shouldn't be placed, and so on. To execute the same query on embedded Cassandra, we call this class execute method. It executes a query with specific consistency level, binding specific values to query parameters and return result set. Please note that this method is static. There is no connection information, no any cluster configuration passed in parameters. That's because the application code is working in context of a database it has embedded. So no database to connect it. This instance is the database. Accordingly, messages for our getMessages implementation could be retrieved from the embedded database by this code. To add a message, a query like this should be executed, and this code is a bit simpler than we would write using the original database library. Looking at the query processor further, we could find even faster ways of executing queries on an embedded Cassandra. Okay, let's move to the implementation of custom in-memory message store. Let's start with approximating the volumes of data it should store. The total amount of data is about these numbers. Only 5% of conversation are active, and only 13 messages of each conversation should be stored in memory. Okay, now we have all the data and can calculate that a fair amount of them should be in memory. These numbers should be further divided to a number of nodes in a cluster and be multiplied to a replication factor. Let's recall the list of all requests the messaging service should implement. Only first 3 methods work with active conversations, so the new in-memory store should implement only these 3. Others touch non-active data and can flood memory with irrelevant roles, as we already discussed. Let's implement getMessages first. A user named Leia opens the messenger and selects the conversation with Luke. I mean, the front-end sends the getMessages request for the last messages in this conversation. The application logic looks for the cached conversation in memory. Well, it's not there yet. Requests messages from the embedded database, places retrieved messages to the in-memory store, and returns them back to the front-end. Feeling some disturbance in the force, Luke opens the messenger too and uses his Jedi powers to route his getMessages request to another yellow replica. The processing on the yellow replica is roughly the same. Messages are requested from database, place it to the in-memory store, and return back to Luke. Caring about Luke, Leia asks him to go for a lunch. That means we have the add request arrived to the blue replica application, inserts this new message to the embedded database and puts it to the in-memory store. The state of the in-memory stored conversation is now like this. All done. The message is sent. Luke gets push on his phone, requests the fresh messages from the yellow replica. The application takes in-memory state of conversation, and Luke gets stale state. No lunch. The galaxy is in great danger now. This is where the data freshness plays an important role. Adding the new message, blue replica should somehow notify other replicas about it so they can refresh their in-memory state. We could use this cluster topology information like we did before for client routing, determine all replicas which could possibly own the conversation and notify them about the new messages by sending a special added request. Then the application would place a new message to the local replica in-memory store. It's not stale anymore and the galaxy is saved now. And it's not. The problem is that this added request is being sent from one replica to another over the network. So all the fail scenarios start to apply here. So this added request could be delivered only to some part of replicas. The rest of replicas could not have it delivered for a long time, depending on what happened to the particular replica. It could possibly crash due to hardware failure for prolonged time. Let's take a look how Cassandra is about to handle the same situation. Executing the insert statement, it determines all the updating conversational replica nodes, builds an update request, the mutation in Cassandra terminology, and tries to send it to all replicas over the network. Because the messenger application and Cassandra database nodes share the same process, this mutation message cannot be delivered to all replicas due to the same failure reasons. In this case, Cassandra stores and delivers messages to the local persistent store. Whenever the yellow replica is back online, all these stored mutation messages are sent to it. This is called hinting. Usually these hints are stored only for a limited amount of downtime, otherwise healthy nodes could run out of disk space trying to store all the messages for a single node's prolonged downtime. So there are other ways of restoring consistency between replicas. They include the read repair, a process of comparing results returned by several replicas on the same query. If there are any inconsistencies detected, mutation message is sent back to the stale replica. And the final way is streaming repair, a background batch process of iterating and comparing through the datasets stored on all replicas. Then mismatched ranges of data are exchanged between nodes. Because the volume to exchange could be large, new data are exchanged in the form of a stable file of the separate streaming connection instead of sending individual mutation messages. These consistency support methods are hard to implement and debug, so it could be wise to not re-implement them for the in-memory store. So what could be much easier is on receiving refreshed data by the database engine by either normal mutation, hint, read repair, or streaming, the database code could notify the application logic which then refreshes the in-memory state to include the fresh data. I mean, we define this apply mutation listener interface in the database code, implemented in the application code, and have it called back by Cassandra. Consider the same case. The mutation message can be delivered by not due to network failure, but because the yellow replica server is crashed and gone to reboot its operating system. Its in-memory state is vanished. Now, hints can't help. Hints contain only the fresh data ever seen by a rebooted node, but get messages need all data lost from the in-memory state and the fresh one. We could get the vanished state data by retrieving them from the database. This retrieval should be performed for every conversation which was active before the replica rebooted. This should lead to the massive spike in amount of read queries right after the node is started. And because reads are served by a quorum of nodes in Cassandra, some network communication occurs for every read, there is a strong chance of catching a cascading failure on the whole cluster. How to fix this? One could use the well-known strategy of having a periodic in-memory state snapshot to a persistent store combined with a commit log of changes between two consecutive snapshots. But again, thanks to embedded database code, we could avoid implementing this from scratch. We create the cache's key space with a local replication strategy. This strategy basically instructs Cassandra not to replicate data on cluster and store it only locally. Then we declare the messages snapshot table here, and whenever data is put to the in-memory store, it is being written to this table. If data is evicted from the in-memory store, it's being deleted from this table. So this table now stores the copy of in-memory state. On node start, it loads the state by executing this simple select query. And this loads a lost state from persistent local storage and hints apply the freshest data a bit later. Loading state from persistent storage can be avoided by using the shared memory to store the in-memory state. A shared memory is not cleared on the application restart until the machine is rebooted. The simplest way to employ shared memory is to open this file. It's better to use a memory mapped file, of course. For Java, ready-to-use structures can be used, implemented in our one new open source library. Sharded memory map and its subclasses provide the necessary functionality. In Linux, the TMPFS system usually is mounted here. We also use the huge TLBFS file system with larger 2 megabyte pages. This makes things much faster. Starting the nodes with the shared memory map, only a quick sanity check is performed on startup now. So start because so fast that the part of the request hit the just started replica before other replicas send all the pending hints to it. And Luke could get stale data from the memory store again. This is because the hints delivery is asynchronous in Cassandra by design. Cassandra reads data from several quorum replicas every time, comparing results returned from every replica to others. So it can detect and throw away the stale data before returning them to client. This heavy read makes the hinting an optional operation, which is not strictly necessary for the consistency. The messenger application gets 15 times more read requests than writes, so it's better not to use such a heavy procedure. So right after initializing the in-memory state locally, we start the embedding Cassandra cluster service and waiting for hints to be delivered from the healthy nodes. Only after all hints are played, the application is allowed to start to accept requests. So that's all about in-memory stores in today's talk. Let's have some summary on them. In stateful microservices, the in-memory store shares the same process with the application and the database. Note, it is custom, and application logic is implemented on it. Application objects are stored in and manipulated in memory of the application service. This allows to avoid unnecessary costs associated with dedicated remote caches. Marshalling and unmarshalling of reads are now easily avoidable. Network costs are not applicable at all. The data freshness is the hard problem for remote caches to solve. We solved it by extending the embedded database engine code with mutation listeners. This allows us to add an application logic on new or updating data, so we could guarantee an in-memory cache data is as fresh as it is in the database. The state loss problem should be addressed for any memory store. We solve it by replaying in-memory updates to the local database table and use shared memory to avoid loading a multi-gigabyte state from persistent store. In stateful services, in-memory caches could have same consistency guarantees as the database, which is very hard to achieve for remote caches. Now let's see how effective the implementation of get last messages request processing could be. This request retrieves a single freshest message for a list of users' conversation. To handle this request, a list of messages has to be retrieved for many conversations. Different conversation could be owned by different application service instances. There are no single instance owning all the data. These message lists should be retrieved mostly from inactive conversations. As we can see here on the snapshot, only one from many of the conversations is selected and active. And this means that these conversations are absent from the in-memory store, and there is no point to load them there. Inactive conversations remain so most of the time. For stateless service architecture, we would have it implemented this way. The client calls get lost messages in the microservice, and then it would retrieve message lists from memcaches for every active conversation, and then from persistent database shards for inactive ones. Contrary, in stateful services, there is no single instance to call. Any single instance is required to make a network request for all data, not owned by it locally, and this implies costs we are trying to avoid. The effective way is to have get-lot messages implemented on all participants here. Microservices have their own implementation, and client has its own. Client's implementation use the service cluster topology information and splits list of conversation IDs to several sublists. Each sublist contains only IDs of conversations owned by a single service node. Then it selects the replica for the first sublist and requests the last messages from it. The same happens for the rest of sublists. Service instance processes these requests, each for its own subset of conversations, and return only a part of response to client. A client waits for all necessary partial responses from services, collects and merges them into the full response. It is essential to call all necessary replicas in parallel to keep duration of the request processing shorter. Now we have to implement the last function for today's talk, the full text search engine. Whenever a user enters some text in the search field, all messages across all these user conversations should be searched and shown to the conversations list view. Of course, scanning for text through all messages of all conversations is not feasible. A total data set of this messenger is over 100 terabytes, so even 1,000 machines cluster cannot make it fast enough. So we have to build an inverted index using, for example, Apache Lucene. A single large inverted index containing all the conversations would not work. This is another interesting topic to discuss, but it's out of scope now, so you have to just believe me. A separate index per user would lead to unnecessary data duplication. Many users participate in any single conversation, so we have to build an index per every conversation, and this index contains only messages of a single conversation. We build indexes up front only for large conversations. For short ones, index can be built right before searching. So let's start with a straightforward implementation. Whenever a user adds a new message, the Lucene index provider add document is called to index it, and we call Lucene to commit the index. This would not work. Too often commit leads to too often merges of Lucene index segments. These merges are both CPU and disk extensive operations. Contrary, do not calling index writer commit leads to too many open indexes because a single service instance adds thousands of messages every second to multiple conversations. This could eat too much memory. A good solution here to be some background process that takes messages not very often. And Cassandra has such background process named compaction. If you want to know about this process in more details, here's the link to read. In short, compaction merges different generations of data flushed at different time to persistent storage. Compaction iterates over data to mesh, always in order defined by row keys. A single conversation is iterated at a time. Messages of a single conversation are iterated in order of their IDs. Compaction is managed by the class named Compaction Manager. We could extend it to call some listener interface. And voila, now the stateful service can do the low overhead massive data processing, and this processing could be used in many other cases than iterating of the full data set is necessary by an application. This is the last crazy trick for today. What I wanted to illustrate here is that embedding database code allows for tighter integration of application and the database, allows to extend the database in the ways necessary for the application, and allows for even more cost reduction across many aspects, not only related to request processing. So we are now the last section of today's talk, the production operations of stateful services. From operations perspective, stateful services also have their own particularities. Let's look at them. The first problem to discuss is longer deployments. This is because of the longer start time of the stateful service. This is because stateful service embeds the database. The database has to perform a persistent data initialization at startup. This initialization time is mainly bound by speed of a persistent storage speed and volume of write-ahead logs to replay. Another thing to wait for the in-memory store loading the lost state from the messages snapshot table. This time is bound by the size of the state to load, frequency of change and eviction events, the CPU power, and so on. The consistency wait time, we should wait for the hints to be played by other nodes. This time depends on the number of skipped mutations. So if deployment process stops and starts instances one by one, the total deployment time is proportional to the total number of instances and could easily last for a day for several hundred instance deployments. So to mitigate this, the deployment process should be not sequential, but parallel, deploying multiple instances at once within a single availability zone. Our deployment process, for example, deploys a single instance first to make sure the new version is not broken, and rest of instances of this zone deploy in parallel. Instances of the rest of zones deploy in parallel at once. This way, total deployment time remains constant regardless of the total instance count and depends on the zones count +1. The second problem is whether we restart database nodes more often. Well, we embedded the database code to the application service, so we restart database node in each zone each time we have to deploy a new application version. Should we mitigate this? Actually, no. This is not a problem for today's fail-first databases like Cassandra. Moreover, these deployments actually test a zone outage on every deployment in the controlled environment and during the work hours. So bugs in a zone outage handling could be detected and fixed early, before the real outage occurs. The third problem is longer scale-out. This is because data is collocated with the application, so to add new instances to the application, data should be resharded. I mean, physically moved over the network to the newly added instances. This problem is not specifically unique to stateful services. Stateless services require resharding to scale out their database and memcache components too. Still, could avoid resharding for the application logic originated CPU or network-bound loads. This urgent needs for the CPU or network consumption by application logic is often related to some new functionality. To mitigate this, capacity planning should be in place. This longer time should be taken into consideration to the, so an application could be scaled out before the load spike hits. To mitigate load spikes rooted in a new application functionality, feature flags could be used for a new code, so they could be employed to cut off the problem code. There could be cases when application sourced load spikes are unpredictable, externally rooted and highly volatile, and the only solution is to have fast afterscale, which implies no resharding is possible. These measures may not help, and sticking with the stateless microservice architecture may be a better approach. This is somewhat the development of the problem I mentioned on the previous slide. This problem applies only to applications which consumption of one of machine resources is much higher than others. Imagine a service which needs high amounts of CPU to do complex calculations for some small amounts of data. Such an application would consume all available CPU on the machine, leaving disks underutilized. It is impossible to install a fraction of disk into a machine, so the underutilized resources of the disk would be wasted. On the contrary, we could imagine an archive service doing very little processing over large volumes of the data. Disks of this service would be full of data, but this machine's CPU would be idling. Stateless services allow each components to be scaled individually, so these imbalances could be mitigated by scaling our stateless service component more for the first application and scaling out the database for the archive one. For stateful, this is not possible. State and application logic are collocated. These imbalances could be mitigated by employing containers and orchestration management systems. They aim to balance resource utilization across the fleet of machines automatically, collocating different containers with different resource consumption properties, keeping distinct resources utilized evenly. A container with high CPU and low disk consumption would be highly likely be collocated by orchestrator onto the same machine with container having low CPU and high disk resource consumption. This would keep resources consumption of the hardware fleet leveled automatically across an organization. We use internally developed one cloud orchestrator for this, but there are several of others available. Kubernetes is one of the popular nowadays. On the bright side, the diagnostics and support of a stateful service are easier than for stateless services because the application logic, the in-memory storage, the database share the same process. It is much easier to diagnose and debug. Setting a breakpoint somewhere in the application logic, one could easily track down the problem to the root of internals of the database and even down to operating system kernel. Running the profiler, one could track down performance problems more easily. Here you can see the example profiler run on a stateful service, showing flame graph for the CPU time spent from the application code here down to in-memory storage stack traces and to the database engine operations here, as well as down to the kernel space here. By the way, this flame graph is built by the async profiler, one of our open source projects. We originally developed it within OK.show. It's low overhead, so we can run it safely on Java servers in production. And we are now at the final slide of my talk. Stateful microservices are more effective and reliable, and application logic shares its cache database in the same process. There is no network between them, so avoid marshalling and network implied costs. The custom implementation of in-memory store avoids overhead costs. Stateful services have an in-memory state consistent with its database state, which is hardly achievable with remote caches. This is not so hard to implement having embedded modern distributed fail-fast database. On Java, the one Neo library could be used to build custom in-memory stores. Stateless microservices was invented more than a decade ago. Problems to which stateless was aimed for could be solved now in new ways. There is a lot of progress during the last years in distributed databases with seamless auto-resharding support and designed to be fail-fast from the ground up. Containers and orchestration systems are good at the process isolation and the hardware-machine automatic utilization leveling, allowing us to avoid externalizing an application in memory and persistent states in remote systems and open a road to build more effective and reliable services.
Applause, please. Unfortunately, Oleg didn't left us any time for Q&A section. So what we do right now you will follow me to the first floor where our official closing ceremony will take place.